our approach is basically to get that IBM mainframe reliability of agents that are running an enterprise, and they're always able to do the same thing with observability on top of it, and basically very transparent execution. I'm Amir Gholami, a research scientist at UC Berkeley, and also co-founder of a stealth startup out of Berkeley called Narada. And today I wanted to share some of the open source work that we've been working on at Berkeley, and then at the end I'll show maybe 1 or 2 slides about what we're building at Narada. So this is a joint work with a lot of great people at Berkeley. Just wanted to shout out to 2 of them, Aaron Erdogan and Nicholas Lee, who've done a lot of the work that I'm going to be showing here. I think a lot of you here have seen demos of agents being able to do tasks, right? So it's pretty impressive when you ask an agent to do something and it goes and operates tools and does it for you. But one of the big problems here is that if you're trying to do things that are beyond just simple function calling, the errors accumulate, right? So the famous example of it was AutoGPT, where you would give it some command and it would start to do things, but then quickly it would diverge and it would do something completely random after a while. And the reason for that is that LLMs that you're using today are doing basically inference in auto-regressive mode, which means that if you're making an error, like even, let's say, 1% error, this error is going to accumulate. And if you're doing tasks that require, let's say, 100 steps, then actually the error is going to be more than 100% because the errors are accumulating in an exponential manner. So what can we do? So one approach that a lot of people in the community are taking are basically waiting for a better model to be designed, let's say GPT-5 or like GPT-6. But we don't think that's going to solve the problem, because even if you reduce this error to 0.1%, still after, let's say now 1,000 steps, you're going to have a problem, right? So we're taking a fundamentally different approach to solving this problem, which is basically how we write code today. So the first thing that we learned when we were writing code was to write code in a modular way, right? You never write a complete application all in one function, right? You basically break things into smaller steps. You basically provide like unit tests around them. You basically build things on top of smaller testable functions. So the question here that we have is, can we design agents the same way, right? A good example of it is hardware, right? So every time you're running an application in your computer, everything gets translated into x86 instruction set, right? Which is basically very, very atomic operations of bit manipulation. And there's errors that happen every cycle, but there's error correction there. There's a lot of like robust mechanism that we've put in hardware that makes it that every time you open your laptop, it works, right? We want to basically build the same thing. Can we build an x86 instruction set architecture so that when I'm having an agent that's taking 1,000 steps, I'm sure that it's doing the right thing? So if you take a look at an LLM, the way we're looking at it is similar to a hardware, right? So I basically renamed this as a logical processing unit. So instead of calling it an LLM, this is like a brain that, given a task, it can basically complete it. It could be any LLM with different capabilities. So it's basically a logical processing unit. So in terms of an anatomy of a simple agent, you basically have a storage. This is your vector storage where you can basically bring information through a RAG. And then you have a context window similar to basically the registers like a CPU has, right? So you have your system prompt, you have some tools, and then you have some data sources that are fed from this vector storage. And then you have this logical processing unit, and then you have an output and potentially some user feedback. So the key question that we asked ourselves was, can we somehow create an x86 instruction set architecture so that this LPU is not doing open-ended stuff? So when you're asking it every day go to my email and just tell me the important emails, it's not just starting everything from scratch in an unstructured form completely. So that was basically the motivation. And so imagine that could be possible, right? So then you can even expand this to, instead of just having one LPU, to multiple LPUs, the same way that our computers have it, right? You have efficiency cores, you have performance cores, you have GPUs, right? So then depending on the task that you have, you can dispatch this to the right set of LPU. So that's basically the direction that we're focusing on. And the very first implementation of that was with LLM compiler, which we presented at ICML 2024, where given a user input, we would basically break this into smaller tasks that we can reason about, that we can basically provide exception handling. We can basically have an LLM as a judge, go and check the output, and make sure that the errors don't accumulate and grow. So basically capture the errors as soon as possible. And we saw great performance. So this was the very first framework that enabled parallel function calling with open source models, right? And we actually was able to get better accuracy, faster runtime, and also in some way, some form of programmable tool calling. So this is an example of how this works. So let's say you have a user query, which is create a calendar invite with Lotfi and Sid at 2 p.m. tomorrow. So let's say you provide this input to the model, And the model obviously doesn't know who is Lotfi and who is Sid, right? So it first needs to go check your contact and see who is Lotfi, who is Sid. Potentially there's multiple Lotfis, multiple Sids, it needs to deduplicate that. So instead of having the LLM in like some reason and act to start to think from scratch and then try to call a bunch of functions back to back in an auto-regressive way, which basically is problematic because the errors can accumulate, instead what we do is the following. So we first create this intermediate representation to an LLM that's basically this LLM compiler that creates this tag of tasks. So basically it first says that the first task that I need to do is call this get email address with Lotfi. This can by itself be an agent because potentially there's multiple Lotfis and I need to deduplicate them and figure out which one are you referring to. The second one is to call the same function but now for Sid. And then once I have their email address, I need to call a third function, create calendar event, which has these like 2 email addresses and then the time. So if we had this, then we can basically create a DAG which basically has the dependencies. So task 1 and 2 don't depend on each other. Task 3 depends on task 2 and 1. And then finally, the create calendar invite, once it's finished, you basically do a join and you're done. So for people who come from a compiler background, this is the same way that we compile code, right? We basically compile the code into an intermediate representation, we perform analysis on that, and then we can actually optimize it. In terms of optimization, these first 2 tasks can be performed in parallel. There's no reason for me to wait. In terms of like optimization, we can perform garbage collection. Because if this agent is going and doing stuff to deduplicate who is Lotfi, I don't need to have that data stored in my context and polluting the information, right? So finally, there is basically a dispatcher which takes these tasks, takes this DAG of task, and then dispatches it to the right LLM. So let's say something requires like a model that's better at math, something may require a model that's just like a summarizer model. But the problem is LLMs are not trained for this kind of a reasoning. So if we see LLMs are great at doing language tasks because we have a lot of data for language tasks, but they're not very good at reasoning because when you have a Stack Overflow, for example, post, people don't put the reasoning that they had in their mind to come up with the answer. So that's one of the problems. But with DeepSeek R1 and recent reasoning models, we saw that we can create synthetic reasoning data and fine-tune these models to become very good at reasoning. So the next task that we had with LLM compiler was what if we can fine-tune a model to perform better planning? Because if you have that better planning, if you have a better IR, intermediate representation, then the rest of it is basically like plug and play. We can basically dispatch these requests and dynamically replan as needed. The key idea here is to create data that can allow us to create that intermediate representation. So obviously this is like how you would do that. Obviously the first thing is don't do any fine tuning, just find a model that's better at that. We don't have a model that's really good at reasoning because there is not enough data for reasoning. You can perform multimodal, this again wouldn't work. Prompt optimization, we did a lot of prompt optimization by providing a lot of instructions, similar examples, but there is a ceiling of how good you can make the model become with just prompt optimization. And if all of these fail, you have to basically perform fine-tuning. And for fine-tuning, you need data. So how do you create that data is the question. So we have another paper on this called LLM to LLM, which we presented at ACL, where the idea is you generate data based on where the model is failing. So let's say the model is not good at, for example, let's say 10-step function calling, right? You provide more examples that involve that 10-step function calling. And so the way that this works is you start with some seed data, you train your model, let's say this is a llama model, and then you see where is the model making mistakes. So similar to how a teacher teaches a student, they see where is the student failing, where is it struggling, and they provide more homework or more examples around those wrong examples. That's what we do. So we basically look at where is the model making mistakes, and then we generate more data using a larger model, synthetic data, and then we repeat this process. And actually, it turns out that this approach is extremely powerful, and without any bells and whistles can provide significant accuracy improvement. The way we do this for agents is basically, you basically create an action trajectory. Let's say you need to have an agent that goes and does like 10 different things, right? You basically need to create synthetic data that does those 10 things, and you have to make sure that those 10 things is basically accurate. I won't go into the detail of this. This is similar to how DeepSeek R1 did this. Basically, you have an ORM model that makes sure the synthetic action trajectory that this agent is taking is correct, and then afterwards, you basically create that intermediate representation from that. So if you're interested, the paper is on archive called Plan and Act that goes into the detail of how we do this, and this will be presented in 2 weeks in ICML as well. But once you do that, without any bells and whistles, just a very simple Plan and Act model, we're able to get more than 30% improvement in terms of accuracy, and this is currently the state-of-the-art for some of the web agent benchmarks using open source models. So this is Web Arena Lite. This is a task where the agent has to go and do tasks on, let's say, GitHub. It has to create a repo, or it has to go find like top contributors of a GitHub repo. And the base model, this is a Quant model, Quant32B model. It gets 9% accuracy. If you perform like some fine-tuning of the executor only, you can increase this to 36%. But once you add that planning capability, once you add that planning module, that intermediate representation module, you can improve the accuracy by 20% with just a very simple loop of creating this reasoning data. And the good thing about this is that we can basically crank this up. Like if you add more compute, we could even increase this further by just creating more data and creating a better planner. So if you're interested, the paper is here called Plan and Act, which will also be presented in 2 weeks in ICML. We also saw similar results on Web Voyager and Web Arena. On Web Arena, we are 81%, 81.36, which is pretty good. The current state of the art is by IBM, which uses a much more complicated approach with multiple models, IBM Kuga, which is 84%. So this is actually, without any complexity, is able to get pretty close to state of the art there. So I wanted to talk now about what we're doing in terms of the stealth startup that we've been working on called Narada. So this is a shameless plug. I wanted to ask the audience if you have enterprise tasks that require high reliability, and the accuracy is important. So you can't just say, hey, this works 80% of the time and it's okay. If you're looking for tasks that require 99.999% accuracy and reliability. And so if you have those challenges, I would love to talk with you and get your thoughts about what we're doing. But our approach is basically to get that IBM mainframe reliability of agents that are running an enterprise, and they're always able to do the same thing with observability on top of it, and basically very transparent execution. So I wanted to show you a quick demo of the capability that we have with our web agent. So if you can play this video. So this is the Narada interface. Basically, if you can just momentarily pause the video. So this is our MVP. Basically, it's like a side pane that you can open in your Chrome, and you can talk with this. So imagine it's ChatGPT that sees what's on your screen, and it can also operate your browser. So I can give it a command. Here I'm looking at a file receipt, and I'm asking the agent to add this to Concur. So the agent is taking control of my browser. This is running in real-time speed. You can compare this with OpenAI operator on computer use of Anthropic. Notice how fast this is, because we create that intermediate representation, and we can reason about things that can run in parallel and execute them in parallel. It even uploaded the receipt, and now it's going to go add attendees. I don't know how many people have done this before with Concur. It's just a pain to add people to Concur. You have to create a new contact every time. So here it's going to add Lutfi and Fernando as attendees. And all of this is basically controlling my browser in real time. This is done basically. And this is G8, so you can actually go and try this live today. The other one is a hotel receipt. For hotel, you have to do tax itemization, right? So you have to look at the hotel and then do tax itemization for every day. It's able to do that as well. So here I just attached the hotel.pdf file. It's coming to the hotel, adding all the fields, uploaded the receipt, and now it's going to do the tax itemization. And notice that the tax itemization is going to be behind the scroll. So the model that we're using is not just computer vision. It also has HTML and DOM. So it sees things that are under the scroll, which is something that currently there is no solution doing that. So it's going to click on itemization, and then it basically fills this out even though it was behind the scroll, because we see the whole HTML. Our model takes that into account. There's a couple more examples of like adding things to Salesforce or HubSpot, but just wanted to show you the capability. Like once you create that intermediate representation, you can do a lot of cool things about it. You can make sure that all the tasks are running accurately. You can do parallel execution, and actually it runs more efficiently and more cost efficiently. So this was a use case where I just copy pasted some notes, and I asked it to add it to Salesforce. And it added the notes, it updated the opportunity stage. And the next thing I'm going to ask is something similar but with HubSpot. So the user doesn't even need to understand, like, how do I do the same thing in HubSpot? It can completely be abstracted away. And the agent can take care of this. So something similar, now with HubSpot, people usually have to do like 2-3 months of onboarding of how to use these SaaS applications. But with this kind of an approach, that completely gets obviated. So this is basically, HubSpot doesn't have call log. Basically, they have this thing called notes. So the agent came to the right opportunity, added the notes, and I also asked it to summarize this and send it as an email. So now it's delegating it to another agent. That's basically the dispatching to another quote-unquote LPU to perform this. So now it's drafting the email. There you go. So our approach in terms of like focus is on enterprise tasks, back office workflows, which require very high volume and require high accuracy in terms of like 99% accurate workflows. So we have these papers on archive. I'm out of time. So if you're interested, the LLM compiler, we've open sourced it. It's available. You can use it. Also, the plan and act is going to be open sourced later next week. Thank you.